So we're interested in long sequences of distinct sets of reals from particular point classes. So this is what Gregor called unreachability. So let's say gamma is some boldface point class. We say some cardinal kappa is gamma unreachable. If there's no sequence of distinct gamma sets of length kappa. So it's sort of a way of measuring the complexity of a point class, like similar to asking what are the lengths of norms in gamma. And I'm most interested in the following conjecture of Gregor's. So he conjectured under 80 plus that if kappa is a regular Suslin cardinal, then kappa plus is gamma unreachable. So this is, the conjecture is optimal. Oh, sorry. Gamma is S of kappa. Thank you. So the conjecture is optimal by some work from the cabal, that particular any Suslin cardinal kappa is reliable. And so if you look at the first norm of a scale witnessing kappa is reliable, that's going to have length kappa. So there are a couple of instances where we know this. They're all in L of R, so we just need to assume, we'll just assume AD plus DC for this talk. Yes. Or no, including kappa. Yes. So Hjorth and Sargsyan showed if gamma is sigma 1 to n plus 2, then delta gamma is gamma unreachable. So this was Hjorth for the case sigma 1, 2, and then Gregor for the rest of the projective hierarchy. And then myself, Itai, and Gregor showed this for inductive-like point classes in L of R. So if gamma is of that form, then the successor of delta gamma, gamma unreachable. And then the result I want to talk about today which is joint work with Itai. So if gamma is sigma 2k plus 3 over J2 of R, that implies delta gamma is gamma unreachable. So a couple comments on this result. First, a corollary is that delta gamma is also the least sigma 2k plus 2 unreachable. So that's just because if you look at a complete norm on a sigma 2k plus 2 over J2 of R set, this has length delta gamma. And then I guess this doesn't include what I've written here, sigma 1 over J2 of R. It just leaves two possibilities for what the least unreachable for that could be. It could be delta 1 omega plus or delta 1 omega plus plus. And it's almost certainly delta 1 omega plus, and it might be, I'd guess you could do it just with similar things as I'll do for these point classes. One other comment about this theorem, there's nothing particularly special about 2 here. The same sort of thing would work with any ordinal, which is a successor or of cofinality omega, where you realize new, where you get new sets of reals. Is there a question? So let me describe. So all three of these theorems use very similar tools. So what do we need? We really need a particular mouse operator. So for all these proofs, we need some mouse operator J. So this is some operator sending X to a mouse M of X. And we need this to have, there are sort of 3 important properties that we need this operator have. So first, correctness. We need it to be able to determine the truth about statements in gamma. So for any gamma set A, we want, there's some formula phi. So that X is an A, if and only if M of X satisfies phi. Yeah? I guess maybe this depends just where you're starting. It's just the next thing after the projective hierarchy. Yeah, I think I'm starting the J hierarchy 1 position later. Yeah. Okay. Yes. Okay. Sorry. Okay. The second, we need some smallness property. So let's say Let's let M infinity be the direct limit of countable iterates of M1j of x. So this is a mouse that has a wooden cardinal, and then the j operator above that. Say delta M infinity is the least wooden of M infinity, and say kappa M infinity is the least less than delta M infinity strong. And we want kappa M infinity to be less than delta gamma. So we have some correctness. This is some largeness property. We have some smallness property here. So we're looking for a mouse in a very particular range. And this is essentially the same. This is a very similar question to asking, is there a mouse whose reals are the set C gamma? And then there's one other property I need. Which is internalization. So we want M1j of x can approximate its own iteration strategy. So this will allow us to define this direct limit, M infinity, inside M1j of x. It's very similar in spirit to what Jan just talked about, though I won't need even as much as he did. So this is sort of the tool we need for the theorem. So what do these theorems need? For the projective case, the operator we wanted was x ascent to m to n of x. For the inductive-like case, we used essentially x ascent to LP gamma of x. And then for yeah, sure, probably. And then for the theorem I'm talking about today, so we'll use the ladder mice. So x is sent to m to n plus 1 ladder of x. So what I'm going to do, basically, I'm going to introduce the ladder mice, and I'll talk about the analysis of Rudiminer, steel, and wooden of these ladder mice. And we'll see it has these three properties. And then at the end, I'll explain why those three properties imply the theorem. It just requires, no, I mean, you just have to be able to approximate what the direct limit embedding basically cofinal in the bottom wooden. You don't have to do like You don't have to put those together at all. So let's define M ladder. So M ladder of X is the least bound mouse containing some sequence of ordinals gamma k. So that first, the gamma k's are cardinals. And second, mk sharp of the mouse up to gamma k is an initial segment of M, and it satisfies that gamma k is wooden. So we have these local woodens, which are cardinals of M and cofinal in our mouse. We need to think about how complex iterability of these mice are. So we say some pre-mouse M is pi1 iterable if for any countable normal tree T on M and any integer K. We have some maximal branch. So that mk sharp of the lined up part of the tree just up to the sup of B is an initial segment of the model you get by choosing the branch B or vice versa. So sort of for example, it agrees with the branches you'd pick using the mk sharps as Q structures when possible. And this is the right definition of iterability below M ladder. So if M if M is sound and omega1 iterable, then M is pi1 iterable. And conversely, if M is pi1 iterable and M is below the ladder, then M is actually iterable. So this is a pi1 definition, so we have essentially that iterability below M ladder is a pi1 condition. All right, I need one more definition. We say M is a putative M ladder if first M is pi1 iterable And second, M satisfies IMM ladder. So we have these putative M ladders. They're fake M ladders with some amount of iterability. And if you co-iterate a putative M ladder against an actual M ladder, the putative M ladder will out-iterate the actual M ladder. I guess maybe is this first order. Oh yeah, sorry. What I mean is it has to be strictly below. So you can't have a. It doesn't satisfy my that there is this sequence of cardinals. Because of this thing, so you can co-iterate the two things, and so long as the pi1 iterability tells you can pick branches which agree with the MK sharps, and if you haven't reached M ladder, then you can put the branches together into a cofinal branch and choose that branch. Right. But if you're strictly below M ladder, then this is not possible, right? Oh, yeah. So I shouldn't have written this as a first order condition. Okay, that's probably all I need anyway, but I thought it was true regardless, but you're probably right. Okay. Satisfy something, and we'll figure out what it is later, and hope. Okay, yeah. So probably this should mean M is pi1 iterable. And M is initial segment of the actual, oh, no. Okay, so you want M is in the reals of M ladder. Okay. Okay, so I think where I was I was saying if M's a putative M ladder, then it out iterates the actual M ladder. And so in particular, we have that M agrees with the actual M ladder up to omega 1 of M ladder. I don't know why I picked the one with the giant handle. That made this way harder. Okay, there's one other part of the analysis of Rudiminer steel and wooden I need. As there's some recursive map, phi goes to phi bar. Such that if phi is a pi 2 formula, then phi bar is a formula in the language of mice. And for any putative M ladder of X, M, we have M satisfies phi of X and omega 1 M ladder if and only if J2 of R satisfies phi bar. So this is close to the correctness I need. I actually need the proof of this. So let me give some idea of how this is proven. Oh, yeah, thank you. So let's let Tx be the tree of attempts to witness that J2 of R doesn't satisfy phi. And note, we have a putative M, this M is a putative M ladder. So it's closed under taking unions of the MK sharps. And so it can determine what projective statements are true. And that implies that it can form a version of what it thinks this tree is. So this TXM is just sort of what M thinks the tree TX is. And so we have TXM embeds into TX. So we want to determine whether inside our mouse M, whether phi holds. We can't just ask about the well-foundedness of TXM, because TXM ill-founded implies TX is, but TXM well-founded doesn't imply that TX is well-founded. So what can we do? We can compare the well-foundedness of TXM against the well-foundedness of trees representing statements that M knows are true. Statements that M knows are true. So what pi2 statements does M know are true? Well, the theory of initial segments, the theory of mice that are below the omega 1 M ladder. So in particular, so let's let SK alpha be the tree of attempts to witness that K is in the theory of M ladder of X cut at alpha. Or that K isn't in the theory, depending on which are true. And then the main lemma for Wooden's theorem is that J2 of R satisfies phi if and only if M satisfies, M thinks that the rank of Tx is below the rank of SK. Okay, so I won't go into the proof of the lemma, but that gives this theorem, and the theorem's almost what I need, right? What I wanted was that sigma 3 truth is sigma 1 over, oh, sorry, for some alpha below omega 1 M ladder. Thank you. And some K, yeah. So what I wanted was that sigma 1 truth, that sigma 3 over J2 of R is sigma 1 over M1 ladder. And what this is giving me is that pi2 over J2 is sigma 1 over M ladder, is definable over M ladder, but is not a sigma 1 formula, right? I have this parameter, omega 1 M ladder in here. And so we have to lift this to give us a formula, which gives sigma 3 truth over J2 in M1 ladder, but we have to be slightly more careful than usual because we want to end up with a sigma 1 formula when we do this. Ooh, I have like 10 minutes. Okay, so I won't go into the proof, but there's a little bit of something to do here because, right, we have to do this. Oh, thank you. We have to do this. We have to get rid of the parameter omega 1 M ladder without going to a sigma 2 formula. But this gives the correctness that I wanted. Our second property was our smallness. So remember, we wanted, if M infinity was the direct limit of countable iterates of M1 ladder of X, M2 ladder of X. And kappa M infinity is the least less than delta M infinity strong of M infinity, so delta M infinity being the least wooden. Then what we wanted was that kappa M infinity is below delta gamma. So the idea is just that iterability of M2 ladder of X below its least wooden cardinal is by Q structures below M1 ladder of X. And then by the analysis of Rudeminer and Steele, iterability below M1 ladder of X is a pi2 condition in J2 of R. So this gives us a simple enough definition of iterability to show that kappa M infinity is small. And then for internalization, what we want is that if M2 ladder is a real of M2 ladder of Y, then M2 ladder of Y can approximate the direct limit embedding from M2 ladder into the direct limit of its iterates. And how you do this is if you look at the rungs of our ladder, so we had those gamma KMs, which were cardinals, which were those locally wooden cardinals, which are cofinal in M2 ladder. Right, so here's M2 ladder. It has a wooden cardinal. It has another wooden cardinal. And it has the gamma k's. Then the ordinals definable by the gamma k's are cofinal in delta 1. And so the gamma k's are the analogs of indiscernibles for the mouse M1. And so if we know where the gamma k's are sent, then we know what branch to choose for the iteration strategy. So that's one key fact. And the other key fact is just that gamma k's for larger mice, you can define what the gamma k's are for smaller mice. So M2 ladder of Y can locate what the Q structures are for iterates of M2 ladder. Okay, I have 5 minutes left. Let me try to give some idea of why these three things imply the theorem. So the theorem, remember what we're trying to show, is that there is no sequence of distinct sigma 3 over J2 of R sets of length delta sigma 3 over J2 of R. So let's suppose we have some sequence A alpha contained in our point class. Let's let Y code M2 ladder. And let's let M infinity be the direct limit of countable iterates of M2 ladder of Y. And then let's let S alpha be the set of conditions Q. And so here I mean the extender algebra at the least wooden of M infinity. So that we have R and N satisfying N is an initial segment of M infinity below its least strong cardinal. Delta N is a cardinal of M infinity. So the least wooden of N is a cardinal of M infinity. Q and R are in the extender algebra at the least wooden of N. And Q and R force in the product extender algebra of N, that the left generic is in the sigma 3 set coded by the right generic. And last, R is compatible with some condition in the full extender algebra of M infinity coding A alpha. And then the key lemma is to show that S alpha actually codes A alpha. In particular, if A alpha is not equal to A beta, then S alpha is not equal to S beta. And from the lemma, the proof is easy. How many possible A alphas can we have? Well, each A alpha is a subset of M infinity cut to its least strong. So number of A alphas we can have is at most the successor of cap M infinity in M infinity, which is strictly below the actual successor of cap M infinity, which by our smallness condition is below delta gamma. So there's our smallness. The correctness, of course, we needed to talk about this, and we needed it sigma 1 because we wanted to reflect realizations of this below the least strong. And the internalization is important because how am I going to say the generic codes A alpha? We say a real codes A alpha if it codes an iterate of M2 ladder and an ordinal in that iterate, which is sent to A alpha by the direct limit embedding. So we needed some internalization of the direct limit embedding to phrase this. Thank you.